Thank you. Thanks for inviting me. I was told to first talk about myself a bit, so I'm not trying to be bragging, but that was the agenda. And then I'll go cover a more technical topic in the area. So yeah, this is my all of my positions I've had. It's unfortunately not a straight line life. It's a lot of curves in there. So those of you who don't know what they should be doing or what they will be doing, don't worry. It actually works out in the end often. So I was actually studying in Germany, not far away from Denmark, for my undergrad. So I did environmental engineering back there, which was similar to civil engineering. So I did a lot of hydraulics and civil structures and so on. And then my PhD I did in environmental fluid mechanics. So there was a kind of a mixture of a mechanical engineering curriculum on heavy on fluid mechanics. So I took, I think, 6 courses on fluid mechanics. And then, but being in the environmental engineering department at Johns Hopkins University. And so we tried to apply fluid mechanics to environmental applications. Then I had 2 postdocs in boundary layer meteorology, so studying evaporation and studying chemical exchange in the atmosphere. And now I'm a professor in mechanical and aerospace engineering at UCSD, focusing very much on energy. And yeah, interesting side note here, I only got this job because the MAE department at UCSD actually had an environmental engineering major in the department. And that's unique. That's almost, I think there's no university that has environmental and mechanical. But UCSD actually has no civil department. We only have structural engineering department. And so civil actually doesn't exist. So that's why environmental is in mechanical. And that's why environmental is more about fluid mechanics than it is about other civil things like water treatment and so on. And so I had that background. I had that background in mechanical and environmental. That's why I was the right fit. Not because my publications, anything else. I think that was the key thing they're looking for at that time. Yeah, but now actually that major is gone. So I seem to have lost my justification for being there, but they cannot fire me anymore, so it was too late. Yeah, so the background is very, very broad and diverse, and definitely not linear. But I started in hydrology. That was my favorite subject in civil engineering. So I liked actually stochastic modeling of rainfall. That was my undergrad favorite subject area. And so I was going to set out to do that for my PhD. So I applied for a PhD at Johns Hopkins. I got admitted. And then I found out, well, my professor actually no longer does any work in that area. So I tried for a while, but of course, being all by yourself, you can't really do much. So I then switched to fluid mechanics. So that was really my mainstay in grad school, fluid mechanics. So learned a lot about fluid mechanics. And that, I think, really defined kind of my brain, because fluid mechanics is a hard subject area. So you really have to study the math and the physics and experimental modeling, other techniques about it. So it's good to study a subject that's maybe boring a little bit, but it's been around for a long time. It's been studied a lot to learn, and then your brain starts thinking in a way that can be applied for many other things. Because after that, really, I didn't do fluid mechanics anymore. So then I worked on solar energy resources and forecasting. So in the 2010s or so, that was a big topic. We were building out solar power in the United States, especially in California. So a lot of funding, and can we map out the resource? Can we forecast for the power grid how much solar power we'll be getting the next hour, the next day? And so that was a big topic area. That kind of died down now. There isn't very much funding anymore in that area. It's mostly been overstudied, I would say, and the industry has taken over in doing forecast models. So now I'm focusing on actually the power grid, power system. So it's more power engineering, it's more electrical engineering work. So I've come all the way from civil, mechanical, environmental, now it's electrical. And unfortunately, I'm not good at any of these. So, but somehow I wiggled my way around here. So. Okay, so let's move on to the technical topic for today. So one slide for motivation. I think you're all familiar with what's happening around us. So we're now a power system that has a lot of solar power on it, a lot of wind power on it in California. This just shows one day, April 23 of this year. And this line here is renewables, which really means solar power and wind power. Hydro is broken out separately here. But it's almost no biomass power or geothermal power. This is almost all wind power and solar power. And back in 2010, when I started this work, they said, well, we can never run the power system with more than 30% renewables. There's too much fluctuations on it. We cannot control the power system very well. Well, now it turns out we actually have 100% renewables. Any power outages on this day? No, because it was running just fine. So now we accept that we can run the power system on 100% renewables. So that's a good thing. But as we all know, solar power is not very stable in the sense that in the evening it drops down to zero. So which means that all of this, what's left here, this is all wind power. Solar power goes to zero. And California has a very solar power dominated system. So we see that we're losing a lot of power every evening because the sun goes down. So good news, it's pretty stable. Not much fluctuations, but bad news, you have a big drop here. And we still have some fluctuations, more so than you would with a nuclear or natural gas power plant. Smaller side here, you see actually the superstar of this year, our batteries. So we have built out our battery fleet in California. And now this line you couldn't see 2 years ago. It was so close to zero we couldn't even make it out. But now actually you see it makes a big contribution. It charges from solar power during the day, and in the evening when solar power goes down, batteries go up, so they discharge in the evening. Yeah.
Could you trace out the battery line with your laser pointer?
Yeah, thank you. Sorry, it's a little bit faint. Let's see, there we go. Yeah, so here, that's the big step here. Here we're going up and then going down again.
Thank you.
Yeah, sure. Hydro is the same. So hydro comes up in the evening, and then nuclear and coal. We only have one nuclear plant left. That's the stable black line. And then we have imports here that also plays a big role. So we export during the day, and then we import in the evening. Okay, so motivation for us is we can use more batteries to balance all this out, and that works for sure. But batteries are expensive, and so other ways to balance this out is with controllable loads. So you can try to shift loads around so that maybe you shouldn't charge your electric car here because that's the worst time of the day. You should charge it over here. Or you run appliances, you pre-cool the building during the day. So there's many options of shifting loads. And so that is one of the challenges of our new power system, as we want to shift more loads, but we haven't done that very much at all. We've just shifted a few AC loads in the past, but not the vast amounts of loads that we have now. So we were part of a team, actually UC Davis was also a much bigger part of the CalFlexHub project, which is about to end, I think, in this year or next year. And the objective of that project was to demonstrate a variety of flexible load technologies. I know that UC Davis, one example was working on fans. So they were studying, could we use ceiling fans to cool rooms and not use the AC? And that way we can maybe prolong time when we can do without AC. So save energy and shift energy around. But our focus was on the electric vehicles and battery storage systems. So we're shifting load with those two technologies. Okay, so here are photographs of those two. So these are typical battery systems. These are shipping containers. That's the classical container that's used for a battery system. This looks a little bit faded because actually this was installed in 2016. It's one of the first big storage systems installed on any campus in the country. So it's, let's see, where is it? 1.5 megawatt system and 1.9 megawatt hours. We actually just got a CEC grant to dramatically upsize that. So this will be taken out now. It's somewhat being fragile in its operating condition. It's now actually will be going to about 20 times that size. So I think 30 megawatt hours and 10 megawatt system. So that's actually too large for our campus. We could power the campus for too long, so it's really more for grid applications. Can we support the grid with that system? And then electric vehicles, I'm sure you've all seen those. Here we did a study with 27 charging stations which are operated by PowerFlex. It's a company that does commercial EV operations. And so we had stations here with a certain kilowatt hour rating. Okay, prices. Of course, nothing works without economic benefits, right? So I've done load shifting for all my life without any income from it. But if you want to really get the masses to adopt it, you have to get the prices right. And so here in the CalFlexHub project, a big focus was on what sort of price curves could we be designing so that in the future we'll be achieving those load shifts automatically without having to tell people when to use power or not. And so they designed different price curves. Here is one example. So there's 4 here that I focus on, but this is the summer highly dynamic price curve. This is actually similar to today's price curve. Today we have a 4 to 9 p.m. peak period. So that's over here. And this just is more granular. So right now, 4 to 9 p.m. is the same price for 5 hours. And that's really not smart because it's much better to use power at 4 o'clock or 8 o'clock than it is to use power at 7 o'clock. And so this highly dynamic curve basically does a more granular adjustment of the price. So the worst time of the day is about 7 to use power. And then all the rest of the day is lower. You also have a little bit of a peak here because of the morning usage. I'll be showing some other price curves later also. Okay, then we try to get this system to work in a more automated way to control these batteries and the EV charging stations. So CalFlexHub has basically a price server, and that's again trying to be a model for the future where we have one price server that's operated by the grid operator, and then they push out the prices. Anybody can download those, any API can access those prices, and then you can pass them on to the consumer. In this case, for the EV charging stations, we actually still have to do manual downloads of those prices and then put them in the load management software, and then they could be used to delay the charging of the cars. For the battery, it was more automated, so we used TCP/IP computing node and then upload the dispatch to the battery system. This field of shifting loads is called optimization. So you have many options. You could charge your car at 8 o'clock or at noon, charge it more or less at different times. So there's no way to really to go through all the options that you have. And so you use optimization. Optimization means you actually write down what is my cost. In this case, it's the economic cost. So the economic cost is mostly this first term. So you multiply the dynamic price. So that's the curve we just saw. That's dollars per kilowatt hour. Multiply that by P. And P is, well, it's too obvious to even list it here. Sorry. P is the power. So you multiply the power that you use by the price, and that tells you what's the cost of using energy at that time. We also have to think about losses. So there's some terms here that tell us, well, if we use the battery more often, then actually we have more losses. So we actually have to use more energy. So we also have to account for that. But this first term, R times P, that's really the key ingredient here. And then optimization, you have constraints, which means you have to restrict what the options are that you can explore. So for batteries, you usually have a maximum and minimum charge state, so it cannot go more than full and less than empty. And same for electric cars. So these are the constraints. And then you can now calculate what's the best way to run my battery. How can I make the most money? So here I'm showing the results for the battery system. Here is 24 hours, August 6th last year. The green line is the price. So that's one of these 4 price curves. And it's one that has a very flat peak in 4 to 9 p.m. here. And then what I'm showing here in blue and red are the set point. Set point is what did we calculate to be the right charge level of the battery. And then in red are the measurements, so how closely do we get with the actual implementation. And that shows power. So in power being positive means we are discharging, and power being negative means we're charging. And so in this case, we're charging while the price is low, and then we're discharging as the price is high. So that seems intuitively the correct choice. That means we're making money off of the difference between this price here and that price here. That difference is what we're gaining by discharging at high price and charging at low price. This shows you the state of charge. So we're charging, and then reaching peak, then discharging during the high price period, and then charging again here. Now this is a different price curve. That's probably the price curve that's most likely to be used in the future. That's called the two-peak high dynamic price. So two-peak means it has a morning peak and an evening peak. So here and here. And really more importantly, it has a valley at noon because we have too much solar power. So we want this price to be low so people use preferential use power at noon. And then it's highly dynamic, so it still changes the price every hour, unlike now where we only change the price twice a day or 3 times a day. And so now we have more options to make money because now we can discharge the battery here in the morning, then we can charge it again at midday, and then we can discharge it again here. So now we can basically charge and discharge it twice a day, so we make money twice a day from these differences between this low and that high, and then this low and this high here. So if we look at the state of charge, and we're charging here, well, the cost is minimal in the morning, discharging during the early morning peak, charging again here at midday, and then discharging again here. So we now make money twice a day. And here's a summary. So we did experiments on 5 days last summer, and then looked at these different price curves, and then this was the profit that we would have obtained if those prices were in existence. Of course, we didn't make that money because those prices are not real. They're just future plans, but this is how much money we could have made at that time. Okay, moving on to the EVs. Yeah, question. Mm-hmm. Yeah, it's the grid. Mm-hmm.
Because in your control and architecture picture, you mentioned like there are EV charging stations and you are doing B2C.
Mm-hmm.
Just wondering like if this battery is also somehow connected with if you are using those batteries to charge them.
Yeah. Yeah, so the idea was to group them together, but really they are in 2 different sites, so they're really operating independently. So the batteries charge to the grid, and the EVs also charge to the grid, and ideally they would be coordinated at the same site, but that didn't exist, so we had to treat them separately. Mm-hmm. Yeah.
When you're discussing the charging and discharging, you're saying that you're discharging like these EVs that are powering the grid too, right? So you're saying that you're making money both times. So then wouldn't the consumer be paying energy twice? Because if you're using the EV's battery to discharge, that means the user has to then charge again, which is costing the end user money. So yes, the company's making double the income, but the end user is also paying double the income, not?
Mm-hmm.
Or is that not how it's working?
Yeah, actually, so no, the first chart that I showed was just for the battery, so there's no EVs yet. Actually, I'll get to the EVs in a second, so we'll get to it right then. But yeah, here you do make money twice here, and yes, you have to recharge a battery, and so you lose money here, but you lose less money than you make. So at the end of the day, you're still making money. I hope that answers the question. Yeah, so good transition, because we're now going to EVs. So EVs are more difficult, right? Because they aren't there all the time. They have small batteries and have to fiddle around with all of different charging stations. But EVs are free, right? You don't have to buy them. They're already there. And so if you find a way that make money and share that money with the consumer, then there could be a win-win where the grid benefits, the site hosts can make money, and the consumer can also make money. But clearly requires more people interaction, more social science skills than the battery. The battery we can just control and don't have to ask anybody for permission. So for the cars, we only did V1G. We did not discharge the cars. That was both a technical issue. These charging stations are not capable of V2G. And that's very common these days. There are very few charging stations that are V2G capable. And secondly, you have all the risk, liability, complaints. Hey, you discharged my car, now the battery's no longer working, or it's lost its size, and so on. So right now it's just a safer bet to do V1G. And so V1G, we always have positive power, so we can charge or not charge, but we cannot discharge. Yeah, so now there are lots of lines here, and that's because with EVs, you have a bit more complicated of a scenario of which way you go about charging these cars. And so we did a couple of different options here. The most intuitive one is what we call V0G. That's not really a technical term. So V1G means you only charge. V2G means you can charge and discharge, so two-directional. V0G, there's no such thing as zero-directional, but it's the dumber version, the dumbest version that's out there. So in that sense, the zero makes sense because it's step zero. You just charge at full power as soon as the car is plugged in. So that's a no-brainer. That's how most charging stations work by default. V1G, you charge, but you vary the power. V2G, it's bidirectional. So that's one option here. So V0G, the red line. So the cars arrive in the morning. So 6, 7, 8 cars arrive at the workplace, and then you charge at full power right away. That means you quickly reach a peak for charging, and then it tapers off later as more cars come in. You still have to charge more later, but most cars are going to be fully charged by around 8. Now, is that a good thing for the environment and for the price? No, right? Because we have this price peak here, and we're actually charging at maximum power when the price is highest. So it's really the dumbest thing we could do, and it costs the most, as we will see, because this price curve is peaking right as we charge the most. And it does not benefit from these low prices here. Yeah, question?
First, would you prefer that we hold questions until the end?
No, go ahead. No, yeah, thank you.
What is the first peak? Like I'm used to seeing the second peak because that's
Mhm.
the transition off of renewable into expensive, I guess more expensive energy. But what's the first peak?
Yeah, it's a good question. What's the first peak, right? We're used to seeing this peak, which is everybody knows now it's bad. Don't run your dryer at 5 p.m. The first peak. So I'm not an economist, so I don't have the correct answer for this question. But I think what happens here is that we kind of over-exaggerate this peak. So I don't think it should be that high based on economic arguments, because we're not peaking the grid at that time. The grid is actually at sort of a happy mid-level power. But I think what we want to do is we want to shift the energy to here. And that's why we exaggerate this to make a bigger difference and shift energy to the midday. That's my...
Sort of like a pricing-driven incentive.
Yeah, I think that's a good way to put it. Mm-hmm. Yep. Yeah, so V0G, that's an easy one. Now, actually, another easy one is constant power. For that, we just took all the energy that came to the EVs. We took the plug-in time, the unplug time, and we just distributed energy flat equally across the whole time interval. So that means charging power is constant, but it's not at peak level. It's just at whatever it needs. That's not realistic because we don't know usually when the car will be unplugging, so we don't know that for sure. But this yellow line is that curve here. And then baseline is when we just charge the cars by whatever PowerFlex uses in their method to charge them. So that's the yellow line here. So that's what happened in real life. It's the yellow line. And then what we simulated now is if we did this optimized charging, where we still took the real EV fleet, we took all the real cars, the real battery sizes, the unplug time and the plug-in time. But now we said, let's use the data and let's shift energy so that we can make the most money or have the least cost, really, for charging these cars. So that's what we call CalFlexHub. So that's the gray line. And clearly the objective of the gray line is to get past 10 a.m. Right? Before 10 a.m. is expensive. After 10 a.m. it's cheap. So we want to shift the EV energy to the middle of the day. And that's why we see here with the gray line, big jump up here. So most cars stay longer than 10 a.m. So they plug in at 7 or 8. They stay, say, at least until noon or even in the evening. And so we can shift energy over here without inconveniencing the driver. At the end of their layover, they still have the same energy in our CalFlexHub line here as they would have in all of these other lines here. So driver doesn't notice anything, but now we did environmental and economic benefits by shifting energy. Yeah.
In these scenarios, were there constraints around how many chargers were available? Did people have to wait in line to charge if they wanted to charge right after 10, for example?
Yeah, right. So that's another complexity in real life. If you did that and everybody jumped on board with doing it, then really chargers will be overloaded. And so that's the other sad truth of real life EV charging. So here actually we only used the charging events that already happened. So we didn't sort of simulate that we would actually get more drivers probably if we did that. Yeah. Mm-hmm. Yeah.
Is this showing, like, from the charging station's perspective or from the battery's perspective?
The EV
The
battery?
reason I ask is because like, an EV is a traveling battery that will experience different areas with different pricing.
Mm-hmm. Yeah. So it's from the charging station perspective. So we did not consider, hey, we could charge in the evening at home or anything like that. We just, just for workplace charging, station perspective. Yeah. Thanks. Okay. So the rest is just taking that data, and we did this for a whole week. So now we analyzed all of these days, and then we looked at what are the total costs. So here's the weekly cost of energy, dollars per kilowatt hour, for these different strategies. So clearly V0G has the most cost, so it's about 27 cents per kilowatt hour, because we charged here during this high price time where we had, putting the price number, but here, so about 50 cents per kilowatt hour is the morning peak price, and so this is higher because of that. And then CalFlexHub is the light blue here, so that's by far the lowest, so we are actually less than 10 cents per kilowatt hour, so it's less than half of the V0G, and also a big reduction compared to these other strategies here. So makes sense. We shifted energy to lower price times, so we had lower cost of charging. Here's another way to put that. Here we're listing what fraction of charging occurred during the low price period. So the low price period is this period here. So how much charging occurred during that period. And then so about 75% of charging occurred at low price period, meaning this was solar power charging, if you will. Whereas for these other strategies, we see a lot less. V0G, only 30% happened during the low price period. Okay, that covers that chapter. Any questions? Otherwise, we'll, yeah. Mm-hmm.
So the high variability, I forget what you called it, HDP, one where it changes every hour.
Yeah. Mm-hmm.
Is that's for like who is like sort of like observing that price?
Right.
If generators are like bidding into the market,
Mm-hmm.
who's like paying for that?
Yeah, that's a good question. So let me back up a bit and talk about how pricing works, because this is one part of the coin, which is called the retail pricing, meaning that's what a consumer, meaning in a business or homeowner would pay. That's what they pay. But on the wholesale market, like I said, that's the other part of pricing, and that's not this, because these curves, while variable, they are still fixed. So we know before the day starts, this is what I'm going to pay. So it's variable, but it's fixed.
Fixed by CAISO?
But usually the CPC, I think, is the entity that actually regulates the price curves.
So they
so the,
set that one where it's
yeah.
like the 3 levels a day?
Right. Yeah.
Okay.
Mm-hmm. Yeah. So it's complicated. There's, I think, rate cases where PG&E has to propose something and it has to be approved by the CPUC. So it's a bit of a back and forth. But that's how the retail pricing happens. And wholesale pricing is also variable, but it's unpredictable. So you don't know what the price will be. So that's why people are more sophisticated when they work on wholesale market pricing, because you're taking risk. Yeah, thank you. That's a good point about pricing in general. Okay, so the last part is more about future looking, where we got a big grant to build a test bed at UCSD, where we can do those things that I just showed you, but in a more automated way. So for this work, I had to spend a lot of hours connecting things and configuring things and feeding in cost functions and so on. This test bed, it's supposedly just a click. You upload your code, and then it will run on the test bed. That project is called DERConnect. It's sponsored by the National Science Foundation, and it's actually an unusual program that many people don't know about, including myself. I didn't know about this, but they have a a infrastructure program, meaning you don't get money to do research, you get money to build infrastructure. A famous example at UCSC is an earthquake shake table. So we built a shake table to test real-life 3D shake motion buildings. And so that's too expensive for any university to just build for one research group and do their own research. So rather it's open to anybody in the country. They can basically apply to NSF to get time on the shake table, and then they can build the building and run it there with the support of the UCC researchers. This is the same thing, same program. So we're really opening up for anybody in the country to do research on. So hopefully some of you will be our customers for this in the future. So a big project, $42 million project. Most of it is going to hardware, but still a lot of people involved here. The background is similar to what you talked about. Many different DERs on a grid, and in the future they will be more controllable. So we'll have water heaters that can be controlled, electric vehicles, air conditioners, even plug loads. And so the question is, how do you orchestrate all of this control where you now have millions of devices rather than hundreds of devices in the current state? And so in the control theory community, you have these different ideas of how do we communicate information in this new world. Do we communicate centrally to all DERs? Probably not, because communicating to 1 million devices and having privacy restrictions and so on is not ideal. So the idea is to do more neighborhood-based or what's called hierarchical or distributed control, where you just locally communicate some information, and then it gets kind of blurred out as you communicate up the chain. So privacy is preserved, and your communication overhead is cut down because you're no longer doing communication to everything at once. So that's the premise of the testbed. The testbed really is composed of two sections. The one is similar to what we just talked about, electric vehicles and so on. These are the real microgrid resources. So we're not building any new charging stations through this grant. We're connecting them to a server, so we can now, say, push out a price curve and then see how the charging stations respond. So we're basically connecting to the UCSD resources that we already have, storage, buildings, solar power systems on rooftops and EVs. And then this here is the lab setup. So that's where we have the controls, communications, some of the batteries that we own ourselves, some islanding where we can island buildings and do more advanced experiments. So this is a new building that we built with this grant here. And then all this is to serve the user. So we have to build flexible architectures. So we don't have to use complicated scripts to connect, but rather we can cater to the user so they can conveniently upload the code to run on the testbed. So this is kind of the architecture of how this all works together. And the center point is what's called a DERMS. That's a DER management system. That means that it's a system that can communicate with all these DERs. It can control the DERs. It can run optimization code on it. It has a database integrated into it. So this does everything that you want your code to do when you do research and optimization. But now, in our case, we don't run on a database or on virtual things. We run on real devices, which means now we have to communicate between this and all of these different things that are in the real world. And so we have a microgrid with the buildings and so on. We still have different applications on distribution systems. We can run distribution system models that simulate voltages on power grids. And then we have some of our own lab test bed here. Buildings, I know it's a big focus at UC Davis, research on buildings. So we did here, we worked with Johnson Controls to just take 12 buildings on the UCSD campus and equip them with very dense metering and thermostats and lighting systems. So we now have 30 air handlers. Those are the machines that pump air through the building. We have about 1,500 LED fixtures, plug load controllers, and then we have these thermostats that do CO2 monitoring as well as temperature, humidity, occupancy. And we now sub-meter here. We sub-meter these buildings by floor and by plug load and lighting, so we can get a lot more granular data, and every 2 seconds metering. So that means we have now good visibility, and we can run experiments by switching on and off light fixtures and running air handlers at different speeds. And that kind of gets us at least to thousands of devices that we can independently communicate and control. So in real life, this is not easy to do. So because everything you have here, your PV, your EVs, your air handlers, they all have different protocols. So that's why this is so hard in the real world, because one person has to write a backnet script and an API script and a Python script. So they have to do everything and know everything. And this probably took us about half the time of our work, is actually going through all the databases, learning all the protocols, communicating with them, labeling everything correctly. So it's quite a nightmare. Even so, we just did 10 buildings. Other people have thousands of buildings. But yeah, so we have to build all of these connectors. So for lighting, we had to build an API connector that connects to the API of the lighting manufacturer, which is proprietary API. And then we use the Brick server, which probably only those working in the buildings area know. Brick server is more of a kind of open source building operating system, meaning that in typical buildings, you actually have a proprietary system and proprietary names of every point in the building. So a thermostat would have a proprietary name. So if you go in, you have no idea where it is and which air handler it feeds and so on. But with Brick, actually, you have a system of how you name things, and you have relational information, which means that if you look at the thermostat name, it will tell you which air handler is controlled by it. So it's logical. It's how engineers or scientists would design a building. And so with this Brick server, we can now make it more easy for someone from the outside to come in and say, yes, I want to control these 10 air handlers. These are the thermostats that control them, so I know where to put in my control signal to get the right response. Now this is more about the management system. So that's the software controls everything. And the key here is that we wanted to build this. We wanted to build a ring. Because here we have all of the DERs. So here's our air handlers and EVs and lighting systems. So they're all in a box. They all are now paired with a system that translates what these devices read. But now this information is sitting here, and we now want to build a system where the user can specify, okay, I want central communication, or I want neighbor ring communication, or I want any other communication that you like to try, which means that this line here can be reconfigured to just go here or to go everywhere. So that's all flexibly configurable. You just have one matrix where you specify, okay, this is my communication matrix. Point 1 communicates with 2, 3, 4. Point 2 communicates with 8, 12, 14. So that matrix, you can make this green line go any way you want to. And this is the lab test bed. So that's more for those who like power engineering things, who measure waveforms and do islanding controls and so on. But this is a one-line diagram. So it's a bus, which means electrical connection. These are switches. And then you can put on different resources. So you have a load bank that simulates load, a battery that can discharge and charge, active and reactive power, a grid emulator where you can simulate what a power grid does. So it's supposed to be also a flexible area where you can basically take a wind turbine and feed its wind signal into here, or you take a battery and feed its signal here, and then see how the power grid reacts to it, and again try your control strategies. Yeah.
So where is the data is processed and stored? Is it in a cloud, a central cloud, or is it like more edge computing type of storage and processing?
Yeah, it's also flexible. So we do have the cloud server. So we do want to store all data in a reliable way, so we don't lose it. But the user has the option of basically restricting the database to only be visible at the edge or within the neighborhood and so on. Yeah. Okay, then talking more about these management systems. So these are the systems that are used by utility companies to now basically roll out and look at more grid applications. So substations, battery systems, and the distribution system, voltage control. So utility companies basically have models of the system, but right now they don't have a lot of visibility and data exchange happening. So they're very into trying to use management systems to actually help them do this management of voltage and power on their distribution system. And so lots of challenges there, some actually very similar to the buildings. There are many different models out there, proprietary models for grid systems. So there's a big effort now by the national labs to use the Common Information Model, which is an open source and standard for naming. So we have that conversion built in. And then visualization. So you take a grid and you overlay it on the neighborhood. You look at say, voltages. And then looking at different applications. So looking at dispatch of DRs. So can we control EV charging to not overload a transformer on the grid? Or do a grid simulation where we look at a bigger grid system and try to plug it into this local system here. And so for that, we did a lot of development also by basically making this more compatible. We call this DERMS Plus because we now have the Common Information Model plugged in here. We have telemetry data surfaces where we can use the data from over here and map it. And then we have different applications where we can look at the typical use cases of utility companies and show them how they would work on the system. So here's one example of the real world where things are very complicated. So a utility company really wants to use all the resources that are on its grid. So all the electric cars, all the batteries, all the air conditioning systems and so on. Which means now you have different what are called aggregators. And so you may have an EV aggregator. That's a company PowerFlex. They have 1,000 charging stations. And they tell the utility, hey, I can reduce my load in the evening by 50 kilowatts. And then they go in and distribute that 50 kilowatts among the charging stations. And then you communicate back to the power grid operator, and you see how that actual load shedding happens in real time. And then another entity may have solar power plants or microgrids. Another entity may have what are called virtual power plants, where you combine different resources together to act together. Another entity may have a building with HVAC and plug loads and lighting. And so now you need to combine all of these different resources, and then you can look at different ways you can modulate these loads to achieve these objectives here. So you could do frequency control on the grid, and then see how all of these resources can follow the frequency control signal. Or you can do demand response, where you try to shed load when there's a high demand on the grid, and see how quickly that can operate. So all these things you can do with the test bed that we're building. Okay, so last slide, summary. This test bed, we're about to commission it actually in next month. So this is perfect timing. We've worked on this for the last 4 years. So now it's 1 more year to go on the grant, but we're planning to open in the first quarter of next year. So for beta testing, and then the full-blown functioning is in fall next year. It's an open test bed, so anybody can use it. So you just get in touch with us, and we work out time and so on for you to use it and try out whatever you want to do on it. Yeah, that's all. Thank you.
Yeah, sorry, my timing can be off sometimes. Go back one slide.
Mm-hmm.
You mentioned something about the frequency.
Mm-hmm.
Is that the actual frequency of the electricity?
Yeah, that's right. Mm-hmm. Yeah, so that's I think why you're asking probably is that's hard to change. You need a lot of power to change frequency. But here we're talking beyond just what we have at UCSD. Basically, you have some loads that you can control, and those would be too small to change frequency in real life. But you could simulate then, okay, if I had 10 times this, what would happen? That type of thing.
Want to change frequency?
This frequency is out of balance sometimes, so it should be 60 hertz, but actually it never is. And so if you actually go plug into the power outlet and you measure frequency, you'll be surprised. So it's generally safe, I mean, it's not bad, but any frequency excursion is undesirable, so the operator always tries to keep it very close to 60 hertz. Mm-hmm.
Thank you.
Yeah, sure.
I have a question.
Yeah.
For project of this scale, how do you manage like users? Like if you you have one student that wants to do this experiment here, and then another person wants to do an experiment that overlaps, or someone wants to do, I don't know, like a utility scale control. There's so many devices. How are you managing that?
Yeah, the question was, how do we manage this test bed in real life where we have many users and they all have different ways of using it. So yeah, I hope I can answer the question in 5 years because it's right now giving us nightmares too. So the good news is it's not like one user would occupy the entire test bed, so it's parallelizable in a way that you can have multiple users doing things in parallel. Of course, they couldn't control the same, say, EV charger at the same time, but probably many users have different objectives. So one would do buildings and one would do EVs. So there's some parallelization built in, but in real life, as we know with research, right, it's hard to plan things. It's hard to tell somebody, okay, tomorrow at 1 p.m. is your slot, and then, hey, they don't make it, and things get late. So it's going to be a bit of a nightmare to make all this happen. But yeah, ask me again next year. Yeah. Yeah.
Yeah, my first question is from the V1 team, where you have done the smart charging.
Mm-hmm.
So you mentioned some optimization, and you also mentioned some of the real world results, right? The savings from by kind of charging the smart charging. So I was just wondering if you can mention some of the like real world challenges with respect to communicating with the EVs when they were connected in their charging station, and also the uncertainties of EV load, like how do you know, like we know the prices that we can see, like, okay, if this is the predicted load of EV and this is how the prices look like, you can optimize the charging. But because you have implemented in the real world, so what were the constraints regarding the unpredictability of EVs availability? And the next is like what were the communication challenges that you have mentioned?
Right. Yeah, those are all great points. So I can see you work in this field too, because in real world things are a little bit more difficult than you show it first. But yeah, so the uncertainty, the biggest uncertainty is what's the departure time of the person, and that generally is unknown. So PowerFlex actually has an app where you can enter what is your departure time, and about 1% of people actually use it. So basically you don't have the information. Now they're working on version 2 where they actually use AI to predict the charging time from past sessions. And DCC actually it's not very accurate because we actually have a large variety in departure times. But hopefully other workplaces are a bit more predictable than we are. So that's a big unknown. And then as a result, of course, you have two options, right? One is you predict a too early of a departure time, then you're fine. You're already full, and you can wait a few more hours. The other way is the bad one, where you depart earlier than you expected, and then as a result, you have less charge than you expected, and then bad things can happen. Yeah, and so at UCSD right now, we haven't done any real implementation yet, so we don't have this problem yet. But what we have done is we built it's called an EV charging club, where actually we now do the full social science protocols. So the people are enrolled in the study, they can receive incentives. They basically sign off, okay, there's a chance you will not get the charge that you want, and they're aware of it. And so we have some safety margins built around it. But we have yet to actually do this experiment that you mentioned which has that risk built in. We hope we can do it next year. But we'll have to see how complaints will shoot us down. Communications, the other question was about communications with the vehicles. So actually only communicate with the charging stations. We do not communicate with the vehicles. That's right now basically the standard. We do not have yet actually the ISO 15158. 15118, thank you. That standard would allow communication between a vehicle and a charging station. It's currently essentially non-existent, but very close to hopefully being rolled out more widely, which means it's easy. You just communicate with the charging station. That communication is already in place because you have to charge the user, so you better able to read what the charging station does. And so that worked quite reliably. Yeah.
Regarding the smart grid, have you studied like upscaling it, or like what do you see in the future? What conclusions do you reach from the study? will it be for just local areas, for small, for microgrids, for example, or will it be like transferable to the conventional
Right.
grid?
Yeah. No, I mean, I think the EVs, that it's really the most powerful way you have, except for big batteries, the most powerful way to do load shifting, right? Because here, basically, you have the two options. One is you don't charge at the workplace. What can you do, right? You have to charge at home. What time do you have to charge? It has to be in the evening or at nighttime. So all bad times, all high CO2 times. So the only way to make EV driving actually environmentally friendly is to do this. And so we kind of have to do it. There's no way around it. If we don't do this, then we'll never reach our carbon goals ever. And so in that sense, yeah, we hope that basically what we're doing here can be used by other workplace operators and PowerFlex and others to basically incentivize people to bring the car to the workplace, to have enough charging stations and charge it there, and then make it happen. Yeah.
Yeah, I meant for regarding the testbed, the last project you
Yeah.
were explaining. I meant the upscaling of that project.
Yeah, not really. Yeah, it's local, so it's supposed you can study bigger things with the simulators, grid simulators, but yeah, we wouldn't say come to UC Davis and say let's partner and do this together. It's just too complicated. Yeah.
So on this plot, it looks like is the CalFlexHub, I guess that like best performing one, that's based off of the charging based off of that hourly changing price?
Yeah, that's right.
Okay.
Yeah, that's the only one that's going off of that price curve. Yeah.
It seems like constant P does pretty good.
Yeah.
I mean, is it like realistic to imagine that people would, say how long they plan on charging their car, or think about that?
Yeah, that's a big question, I guess. So I don't know the answer to that. What do you think, Alan?
The behavior part is very interesting. I will say there are a lot of like smart charging pilots in the country now, and they have done actually pretty crude things that have actually gotten people to participate, to like be willing to participate, essentially. So, a lot of these pilot programs are converging on like, oh, we'll pay you $10 a month, and then whenever you plug in, you're going to let us control, but we'll give you a certain threshold, we'll let you opt out a certain number of times, and when they do that, it seems like you're getting like 90+% participation. So it's almost you're taking some of the decision making out of the consumer's hands, where they don't have to worry about it, and you let them control, and you just give them a little bit of incentive to do that. At least that's.
Okay.
I feel
Yeah.
like a lot of the pilot programs are kind of congregating on that.
Okay, nice. Yeah. Yeah, and just one more comment. Keep in mind the constant P here, that actually is also not realistic, because that also requires knowing the departure time. And so we don't know it, so really that's not really a fair comparison in a way. Yeah.
So for the first project, battery storage, so my understanding is you're optimizing for short-term or daily profit.
Yeah, that's right.
What if you take into consideration like battery lifetime? Is there other things you will do to force batteries like last longer?
Right. Yeah, so you're right. If you do the full economics, there's every time you discharge a battery or charge it, you have a degradation, and you shorten your life, and so that also needs to be taken into account. Yeah, with these differences in price here, you basically have no worry about that, because the difference is so large that the degradation is a tiny cost compared to that. But yeah, in real life, the wholesale market, that's a whole different story, because their price differences are often much smaller, and then you do have to worry about degradation and costs associated with that. Yeah.
What factors are like the drivers of degradation? Like is the
Oh wow, that's a whole whole seminar in itself. But yeah, it's the so what, I'm not an expert in this, but from what I understand is the charging power. The more power, higher power you have, the more degradation and temperature. If the battery is not conditioned to be at the right temperature, say too cold or too hot, especially, then you have higher degradation.
Depth of discharge.
Yeah, depth of discharge also. Yeah, yeah, that's right. Thanks. Yeah, some studies more on electric cars, actually, electric car studies on basically how the battery thermal management system has affected different car makes differently in terms of degradation. So Tesla versus Nissan and so on. Yeah. Yep.
For DERConnect, so like you had to do a lot of upfront work to create really deep metering in buildings and with, create a lot of relationships with like CalFlex and like also the utilities and making sure that it's all connected well. It's really important work in terms of like looking at how we can do microgrids, but how realistic do you see that going beyond like the UCSD campus and having that ability to have that connected grid infrastructure beyond, right? Because universities are in a really interesting place where they can have hundreds and thousands of buildings where it's all centrally controlled, and they can do that load shifting and other things. But yeah, I guess like how do you see that expanding beyond the test bed?
Yeah, that's a great point because you're right. It's not worth it to do this for one building or even 3 buildings or 10 buildings. So only really an Apple or a UC Davis or can really do this and justify the investment cost there. But yeah, the goal is something I really haven't talked about today is that there are going to be standards, and like OpenADR is one protocol that's basically now required. I think, and correct me if I'm wrong here, but I think the CPC requires OpenADR to be built into any building and other energy management system, which means you now have, you get around all of these proprietary things. You now say every light fixture controller has to have OpenADR, which means that if I build a server to control energy loads, I just send a signal to that OpenADR compatible system, and then you get around all of the work that we had to do here. So, which means that, yeah, right now it's still hard. The hope is, and maybe in 5 years, 10 years, it's going to be easier. And here with our testbed, we're building a testbed where we can try out the control methods rather than the control protocols to see what kind of control method works best. And then once the real world is ready, then we can apply the methods to the
Because I know at Davis, like we use Siemens, and it's all
Yep.
proprietary, and so it's, we're running into issues now already with
Yep.
trying to create visibility just in our buildings alone. So,
Yep.
okay.
Yeah, feel the pain. Yeah, we have transfer controls, but it's the same thing. Yeah. Yeah. Yep.
Just a clarifying question. Your test bed, you guys like you were mentioning like you have simulated and some of the things were there like in the lab and that's quite funny. So I'm just wondering like in simulations you can simulate the grid part and also the DR parts, right?
Yep.
And what about the lab? Is it like something similar happening in the lab, like in the real test bed, like the DRs there and controlling and then looking here at the facts and then or something?
Mm-hmm. Yeah. So the lab was also designed to be flexible like that, and the way we do that is what we call an emulator. An emulator is basically a combination of an inverter and a battery, and what you can now do is you can emulate any signal through this here, right? Because the battery can do anything that any other device on the grid can do. It can discharge, charge, real power, reactive power, fast or slow, and so that means that you can use that tandem of devices here to basically do anything that you wanted to test. And so example is UCC has no wind resource, so there's no wind power plants on campus, so we couldn't even use wind power here. But if you had a wind turbine that you wanted to test, then we could make this emulator be giving us the same signal as your wind turbine does. Yeah.
So, not my area, so sorry if this is a really dumb question, but is there ever a case where it's like the control system uses more energy than what you would say? Because I'm thinking about like
data center. Yeah,
centers
right.
and-
Yeah, in the old days I would say no, never. But but yeah, after reading the news for the last few months, I'm getting more worried about it too. Yeah, I mean there's different types of control systems. So yeah, if you use those based on machine learning and so on, then I'm sure you could construe a scenario where they actually do use more energy. But yeah, my colleagues are good mathematicians, so they like to use convex systems, and those actually take very little energy to solve. But yeah, clearly, yeah, but in a real world, if you have millions of devices, actually these control systems get very large and very hard to solve. Yeah, so I don't know the answer, but it's definitely worth keeping it in mind when you do controls. Yeah, thanks.
So, what happens to the grid, since the future appears that the grid is going to be inextricably, it's going to be very tied together via just like a ton of data connections that need to be transmitted between each other, like over the internet or by direct wire. What happens to the grid when the internet stops?
Yeah, that's a good question. So there's different types of communication systems. So utilities actually have their own communication systems that are not relying on the internet, and so the nightmare scenario is not going to happen the way you think it will be. But if we go more into our world of DERConnect, where we have millions of devices, those will not have their own systems. So there will be sort of a parallel architecture, and then yes, then it could definitely be affect not having internet. What probably will happen in real life is that you have a scheduling system where you upload schedules to devices, and then if the internet goes down, you still have the locally stored schedule, so you can basically survive a few hours on that old schedule. You would not be able to update it, but maybe that's fine for a few hours, and that probably will mitigate most issues. But yeah, if things go really bad, then yeah, eventually we may have to acknowledge that we have some limitations in our systems. Yeah.
Okay, cool.
Yeah.
So just a very interesting question followed by TOEFL. So as we know that this year's Nobel Prize was some part of contribute to the AI part, right? So for this UCSD project, what do you think about utilize the AI into your control system? What's the future for this in your perspective?
Yeah. Yeah, I mean, there's no doubt about it that it will be a big contribution to the future system. So we are agnostic. We don't care about if you want to do convex systems control or if you want to do machine learning or data-driven control systems. So we may not have all the computational power for you to try anything you want to, but if you give us the signal and the models, then we can definitely run them there. Yeah, so we're agnostic to that. We're definitely very interested in doing research with data-driven control. Yeah. Yes.
You were mentioning some of the buildings that you have included in the flexibility. I'm just wondering, is it just like the HVAC, or have you included some of the other roles? You guys have included the lighting, but maybe some plug roles or all those other rooms in the building. And what are kind of the challenges? Because I know with HVAC, it's a little bit easy because they have all those schedules and things.
Right.
So you have all those, have you included some of the other roles and the challenges with the control maybe also?
Right.
Because again,
Yeah.
the open area question, they don't, for some of the roles you cannot access them with APIs or cannot send the signals. Is it something that is happening here? Or how do you kind of see that?
Is your question more about the communication architecture, or is it more about the people using? Yeah, okay.
Communication.
Yeah, communications. Yeah, you're right. It has to be custom built, like our plug-load controllers. They have a BACnet server, so we have to use BACnet to communicate with them. But then with lighting, they have a proprietary API that we have to communicate with. So yeah, all had to be manually programmed. We're not using OpenADR in any of these because it was too late for us to make it part of it. But yeah, it's a bit of a challenge, but it's not insurmountable, right? Many people use the APIs for lighting controls, so it's definitely doable. Just have to spend some time to make it work. Most things in buildings are BACnet, so that's the main workhorse, I would say, for communications with most of these devices. Yeah.
Have you tried the bidirectional energy flow?
For EVs?
Buildings? No,
from
from the buildings to the grid, or the other way back, like by
Mhm.
the.
Yeah, right.
having-
No, we haven't. So actually, our buildings don't have energy storage, so we couldn't even do it. But and I know it's a big focus right now with like doing V2B, so vehicle to buildings, and then you could also have buildings export power. But yeah, in our case, we just didn't have the option of doing it. Yeah.
I'm curious about in cybersecurity area. This system can be hacked or be used like a security attack or not?
Right. Yeah, it's definitely a big concern. Also, not my expertise, so I can't really give you any more than a layman's answer to it. In our case, the answer is it's pretty hard because UC has pretty good tabs on who logs in, surprisingly, given all the people who are on campus. But it's actually pretty hard to hack the system because it's the multi-factor authentication and then they have certain portals that are IP numbers that are limited, right? So there's a lot of things you can do to prevent attacks on the system. Yeah, out in the real world where things are not maintained well, definitely a big risk.